Our meeting, our colloquium. So today we have presentation by Sophie Musset about electron acceleration and solar jets. So Sophie obtained her PhD from Paris Observatory in 2016, working on the acceleration and propagation of accelerated particles in the solar corona and for preparation of the STIX experiment on solar orbiter. Then she moved to United States and spent 3 years in the University of Minnesota, where she worked on the Foxy sounding rockets with Lindsay and other collaborators, and studied particle acceleration in connection to coronal jets. Now she moved back to Europe, to University of Glasgow, to work on radio signatures of energetic electrons escaping the solar corona. So, and now we have Sophie's talk about coronal jets and electron acceleration. So please, Sophie, go ahead. I will issue a warning 5 minutes before end of the talk, which is 45 minutes total. To everyone, please keep your microphone muted and video off. Okay, please, sorry, go ahead.
Yeah, thank you for your introduction, and good afternoon, everyone, or good evening. So I thought I would start a bit with reminding what are jets, and then go back to what we know about energetic electrons in connection to jets. So coronal jets, the early observations of coronal jets were made in soft X-rays. And so we have here an example of observations. I'm not sure, can you see my pointer, mouse pointer?
Not really.
Well, so then I will describe just with words. So on the right, you have several images taken at different time, and you can see on the panel that is encircled with blue, that have some structures that is ejecting from this patch. And so that's the first, or maybe one of the first jets that we're seeing. And when you continue to look at this time sequence at the end, in the last panel, you can see that the patch is now kind of divided in two small patches. And so that was used for by the people that look at the event to say that there was some magnetic reconnection that must have happened and created this separation. So they made a simple model in cartoon, as you can see here. And they really expected that this jet was rising from magnetic reconnection between a closed structure, a closed loop, and some magnetic field that was open to the higher solar corona. So this is one of the earliest observations. Now jets are kind of seen very frequently. So they are seen also in EUV, as is shown here. So we define coronal jets are collimated ejections of plasma that are generally seen in soft X-ray or extreme ultraviolet because they are composed of hot plasma. They have been seen in coronal hole boundaries, in the quiet sun, and in active regions, and sometimes in connection with solar flares. So they really are everywhere on the sun. And you can see them with various shapes and scales. And so they are a phenomenon that is recurrent on the sun. And they do seem to follow open magnetic field line. This is why we see the plasma being ejected from the sun. And so we think they may offer a path for particles to escape the solar atmosphere, especially because of this, the fact that we have magnetic reconnection. We expect particles to be accelerated during this process. And so if they have access to the open magnetic field line along which the jets are escaping as well, then those particles can escape the solar atmosphere and eventually maybe being detected in situ in the heliosphere. So this model that is the early standard model for jets is called interchange reconnection because it's changing from an open to close to open magnetic field line. Compare this model with the standard flare model as we have here. So on the left, you have a jet model, and on the right, a standard flare model. And they are very similar because we have this idea of magnetic reconnection being as the start. So here you see the X point, which is where we have magnetic reconnection, and we expect to have reconnection jets that are emitted at the alpha velocity of the plasma. Following those jets, they will collide with some magnetic structure and form fast mode MHD shocks. And those shocks will be responsible for plasma compression. And in the case of the jet, that's where we have the formation of the hot coronal jet that can be seen in X-ray because of the temperature of the plasma. And the speed of these hot jets is comparable to the sound speed of the jet plasma in this model. And of course, because we have magnetic reconnection, we expect to have acceleration of particles, and the energetic electrons will propagate toward the sun surface, following the feed lines of the closed structures. And when they reach the bottom, the foot points of the structure, they will produce the Bremsstrahlung X-ray emission, which is very commonly seen in solar flares, and sometimes seen also in jets, as I will show you. Difference here, as you can see, is that in the standard flare model, we expect pairs of foot points, but in the jet model, we expect to see 3 foot points because we have this structure that is typical for jets. More recently, jets have been studied in different MHD simulations, and this is one example. This is kind of a different idea from the interchange reconnection model. Here, it's a comparison between what happened with a CME and what happened with a jet. And this, in this model called the breakout model, we can see the formation of a filament that will then erupt. And this will be the same process for CME and the jet, but of course on a much smaller scale for the jet. And so in this figure here, you can see the filament in yellow being formed over the time and then being ejected as the jet. So this model is actually asking the possibility if jets could be mini filament eruption, if all jets would be that way, or if at least some of them would be mini filament eruptions. And some observations are actually supporting this idea. You can see here an observation also with the AI instrument where we have a jet, but showed by the small arrow, you can see a small and dark structure that is believed to be a filament that is first low in the corona, and then that can be seen escaping the sun with the hot plasma. A coronal jet, as I said, would probably be a good way for particles to escape the solar corona. And to test that, we could try to find if there is any occurrence of jets that correspond to the different signatures that we have of energetic particles, and especially of particles escaping the sun. So just as a reminder of what those are, we typically believe that we have magnetic reconnection in the lower part of the solar corona. And then particles are accelerated, and electrons in particular would produce many different diagnostics. If they are traveling towards the solar surface, they will produce this X-ray emission via Bremsstrahlung. and they will produce also diode synchrotron emission in radio. If they escape on an open magnetic field line towards the interplanetary medium, they will produce a radio burst that can be seen as we can see in this the frequency of the radio emission is drifting over time, and this is because the electrons are propagating at and evolving in a different density over time, different plasma density over time. And of course, we also can detect sometimes if we have the probe at the right place, we can detect those electrons are in situ directly in the heliosphere. So jets have been already identified as sources for particle events that were detected in situ at 1 AU. And I show here one example, but there are several studies on this subject. Here we have an example of electron and solar energetic particle event that has the particularity of being a helium-3 rich event. And this is actually from a study that was studying 26 of those events. And they saw that they were associated with type 3 radio bursts, so with propagating energetic electrons escaping the sun, and with electron events, so energetic electrons detected in situ. They also showed that they were associated with weak solar activity at the source location. So not big flares, but just small eruption or jets, or also in some cases AUV waves. And the one thing they also note is that there is only weak or maybe no correlation between the properties of the solar sources and the energetic electrons. On the side of energetic electrons in particular, people have also looked at correlation between energetic electrons events also detected in situ and jets. So this is from a study from Kruger et al., where they have 16 prompt energetic electron events, and they selected it because they were associated with non-thermal X-ray emission, so they knew the source was in the low corona. And for those electrons, it was for AIS, so there was not always good EUV images of the source. But when there was trace data for those events, they always found jets. But it was only for 6 of those events. So they had 16 in situ detection, and only for 6 of them, they had the good imaging in EUV. But for all of them, they saw a jet in the EUV data. And also for all of them, they made the X-ray imaging. And so in most cases, 3 foot points in hard X-ray. And so you can see those as blue contours on the images. And so those foot points, the fact that we have 3 foot points is really one of the good signature of a jet, because as I showed in the cartoon earlier, when we have only a flare, we expect only 2 foot points. So the question arises, is this just that they were lucky enough to find jets or signature of 3 foot points each time, or are jets actually kind of always associated with energetic electron events that we detect in situ? On another note, we can also often see the jets associated with type 3 radio burst. And this is one example here from a study from a few years ago, where jets and EUV jets and also soft X often associated with those type 3 radio bursts. And you can see it on the time profile. Those numbers that are in the time profile represent the jets, and you can see that they correspond to type 3 radio bursts that are clearly seen in the bottom panel. More recently, Parashiv et al. Made a study of jets that were recurring in 6 different regions, and they saw that they were very well correlated with some type 3 radio bursts that were detected also in the interplanetary medium. So in those 2 examples, we have a correlation between jets that are emitted in the low corona or visible in the low corona with type bursts that are measured at frequencies that correspond to very high corona or interplanetary medium. So the next step to make sure that those things are related is to look at type 3 radio bursts that are actually emitted closer to the source of energetic electrons, so the site of acceleration or the jet itself. This was done by, for example, a paper from Lindsay Gleisner, where she used the data from the NANSER radioheliograph. And with this instrument, we can even do images of the radio burst, and that is very useful to associate with its source. And here you see an example. So the centroids of the radiuses are in the triangle and cross symbols. And you can see that they seem to follow a magnetic field line that are connected to the jet that we see here on this data. Another example more recently, well, not that much more recently, but is from the study of Chen et al., where the VLA was used to make images also of the type 3 decametric burst. And on this data, we can see in grayscale again the jet, and the color points or dots are the centroids of the radio sources. Again, the color scales show the change in frequency. So the higher the frequency, the closer to the source we are, which clearly show that electrons are escaping that region and they follow the line that is started by the jet. So here again, a clear link between the jet and the escaping energetic electrons. And we are so closely associated. What we want to see is the electrons may be in the jet itself. This is actually not very easy to do. One could look at the X-ray signatures of those electrons. This was done in this example from the same paper from Gleisner et al., where we see here the X-ray emission in contours. And on the third panel, we can see some high energy emission, so probably from non-thermal electrons that seems to be really associated with the jet itself that we see in gray. And so this is quite difficult to do with the current instrumentation, I mean, with the RESI spacecraft, because RESI didn't have a really good dynamic range. And so you can see here that this was done where the flare was occulted. So the bright foot points were not partially occulted. That was kind of helping to see the emission that probably is fainter from the jet itself. Study recently done was combining those X-ray diagnostics with the gyro sequential emission from the flare and some modeling using the GX simulator. And so in this study, combining those observations and fitting them with the model made possible to characterize the full electron population in the jet itself. And you can see here in the panel, just between images and spectra, you have a panel showing the 3D configuration of the jets. And when you have the flare loop and you have the jets that is shown with the small j, and you see this blue distribution that is representing the jet and the electron population that was simulated from the data. to fit the data. So those are really state-of-the-art observation of electrons directly in jets connected to flares. What I've been involved in is trying to see how often this could be done and how often we could see energetic electrons in those jets. To do that, I selected as many jets as I could that were associated with flares that were observed by RESI in the AIA era. And so you have here two examples of jets, and on which I have overplotted some the X-ray emission. And for those jets, we performed the X-ray spectroscopy to try to find if there was any non-thermal emission from those electrons. And we came with this observation that we could find a non-thermal components in the X-ray emission only in 25% of the events that we have studied. So this seemed not a lot, but we have to keep in mind that those events are really kind of small. They are associated with mostly B-class flares, and it's possible that the component, the non-thermal component, is not pronounced enough to be detected by RESI, since RESI has some kind of a high background at this energy. So that might be one reason why. And then we also try to see if the properties of jets were associated or related to the properties of the flares, the flare that produced these electrons. So this is just one of the summary plots that we have, but over the 33 flare-related jets that we had in our study, only 6 of them, 8 of them have a clear non-thermal component. And as I said, this is maybe because we are looking at B-class flares, but also we didn't find any correlation, any obvious correlation between the flares, which were mostly the intensity in soft X-rays and its thermal energy, and the jet itself. So we look at the duration of the jet or its velocity, and there is no clear trend between the two, which kind of, if you remember in the study from Nita et al., where they studied the relationship between the property of the ECP event and the jet, they also didn't see any correlation, or only weak correlations.
Sophie, can I ask a quick question, just clarification? On this plot you have on the left, which of those flares actually had non-thermal component? Or did you mark that?
Yes, those are with the squares, the black squares around.
Sorry, the black squares.
Yeah.
Okay, because some of them. Okay.
And the color scale is the position on the solar disk. So the blue ones are close to the center, and the yellow one are on the limb. And you can see there is not also even in that distribution, the ones that have the non-thermal part clearly visible are also scattered all over the place. They do not correspond. I thought maybe they would correspond to faster jets or something, but that is not the case. Right. That's at this point we have still some very interesting open question, I think, on this subject, because we have seen those associations in a few cases that are very well defined. We have seen, I started the statistical analysis only on 33 events, and we still have this question open. So are jets always present at sources of electron events? As we have seen the Krüger et al. Paper, those when they took prompt energetic electron events detected in situ, they kind of always found jets, but it was only a few events that they look at. So that's that's still an open question if this is really always the case. And how often are jets associated with escaping beam of electrons? When we see type 3 radio bursts, do we always expect a jet being at the source of those? And what is the relation between the properties of the jet and the distribution of non-thermal electrons? According to my preliminary study, there is not a strong link between relationship between those properties. But I have to point out it was since we have a huge scatter on those values, I think it would be interesting to revisit that with a lot more events. And the open question that is, are jets all small-scale CMEs, and that is mini filament eruptions? And I think all of those questions are really a good science case for Solar Orbiter and Parker Solar Probe. One of the science objectives of Solar Orbiter is to understand how the solar eruption produce energetic particle radiation that fills the heliosphere. And jets are really one of the key elements to understand how those particles are, in particular, escaping the solar corona and filling the heliosphere. And in the solar and the Parker Solar Probe era that has started already and is really exciting. We will have all those diagnostics that I've been talking about, but with, in some cases, much more sensitivity. Because we are going closer to the sun, we will have more sensitive observation. On the in situ, especially in measurements, we will be closer to the sun, so we will be able to detect weaker events, which seems to be a good thing to study jets. Jets seems to be on the weaker side when we compare to flares or CMEs. On the X-ray point of view as well, STIX will provide data with a much better sensitivity than RESI, so we should be able to see signature of very faint events, and we could see if, in particular, the non-thermal parts that we couldn't see with RESI is there in those faint events, or if it's really the case that in jets sometimes we cannot efficiently accelerate particles and we don't have this strong non-thermal part. We will also have, of course, the radio diagnostics that will be from both the onboard instruments, RPW and fields, but also completed with the ground-based radio observatories that we have today that cover a huge span of frequencies, and so that allow us to really follow electrons from the site to the in situ detection of electrons. And I also added something I didn't talk so far about, but we will have those vector magnetic fields that are measuring the photosphere. This is important to people that are modeling the jets and trying to understand what the magnetic field configuration will actually lead to jets. So all of combined together will produce, I think, very interesting cases for us to understand more about jets. Another thing that I want to mention is the problem of jet velocity. So when I had these 33 jets to study, I tried their velocity, and I was doing so on the EUV data from ARA. So it is not spectroscopic measurement of velocity, but just the velocity of the jet projected in the plane of observation. So this was done on a time distance plot. You can see an example here. And as you can see, first, one jet is not just something ejecting one time. Here in this example, you can see multiple ejecta, and they don't have all the same speed. But I try to look for the one that maybe was extending the most or that was intense, and estimate the velocity in that variation that is shown here with the white line. doing so, since I had a few events, I could do some statistics. I could see this is the distribution of jet velocities. So you can see that we have very fast and very slow jets, but there is a peak, and the mean velocity is about 200 kilometers per second. And this is actually comparable to a velocity average of 270 kilometers per second that was found on 20 jets in active region on a paper by Muller et al. But that velocity is kind of interesting because this was measured in the 304 Angstrom channel, where the plasma that is emitting in that channel is supposed to be kind of low compared to the corona or even the flare plasma. And so at this temperature of 10 to the 5 Kelvin, we expect the sound speed to be 50 kilometers per second. And so I put this limitation here on the graph, and we also have a value of the chromospheric evaporation upper limit for plasma from the chromosphere derived from Fischer et al. And you can see that most of the jets have velocities above those two limits, which is kind of interesting since we expect the jets to be traveling at the sound speed from early models of jets. But that is actually something that was observed by someone else. So I show here a study from Matsui et al. In 2012. They studied this time velocities from spectroscopic measurements in UV in different channels, and they are all shown here as a function of temperature. And the lines that are shown are the sound speed as a function of temperature and this chromospheric evaporation speed that I was talking about. And you can see that all points seem to lie in between those two lines, all except one. This one, which is actually corresponds to a temperature of 10 to the 5 Kelvin, so very similar to the 304 Angstrom channel. So it seems here that the cool plasma will go faster than the chromospheric evaporation velocity limit, and that raises the question that maybe cool plasma is tracing the propagation of galvanic perturbation. This is actually discussed in some simulations of jets, in particular the simulation from Etienne Paria, where the driver of those jets are propagating galvanic waves that will develop on open magnetic field line. And they run those simulations with different parameters, but when it was at a low beta, plasma beta, the propagation speed of the wave was very close to the ambient Alfvén speed, and that was much higher than the bulk flow speed of the plasma. So I thought this was an interesting observation that shows that plasma velocity could be an interesting tool to understand exactly what is driving the jet. So jet velocities, timing between jet and signature of particle acceleration, the number of X-ray footpoints, and the energy budget between accelerated particle and jets will all be very interesting observational constraints for jet models, and maybe will help determine if there are differences of prediction between the interchange reconnection and breakouts model, for example. Okay, last maybe topic for this seminar is I think we need a corner jet database. Most studies that I have shown here focus on a few cases, maybe the base cases that were found for jets. We have seen a few statistical studies, but usually they have less than 40 events. And since the jets have very different shapes, velocity, durations, settings, etc., usually the scat for those statistical studies is non-negligible. And since those jets will come in so many different shapes, both in observations but also in simulations. You can see in simulation of jets, if you change the settings a little bit, like the inclination of the magnetic field or the beta of the plasma or anything, you will change your observation of the jet, and you could actually simulate a straight jet or a blowout jet with the same in the same model. So I do think we need an extended jet database to be able to find many observations that could be used to constrain the models and to understand. So not only to understand how the jet arise and what is the physics behind the jet, but also what is the relationship with the particle acceleration, which what I've been focusing on more. To do so, we propose with a collaboration to do the citizen science approach. We will ask volunteers from the general public to look at AIA data, and we choose to look at 3 or 4 angstrom images, because that is where jets are often easy to spot because they are bright compared to the background. And so we will ask the volunteers to inspect this data, to look at movies, and to report the jets that they see in the data. So this is something that is hosted on a platform that is called Zooniverse, where they have many different science citizen projects. And we are in the last step of the preparation of the project, so it should be launched early next year. And I would, of course, appreciate if anyone at this point where it will be announced, if you can follow the announcement to any students, any people that would be interested to participate. The goal of this project is really to build a nice database of jets where we will have we ask the people to report their time where the jet begins, the time where it's ending, and the location of the jet. But we also draw a box around the jet so that we also have an idea of the extent of it. Okay, so the conclusion here is that there seems to be a clear link between coronal jets and the signature of energetic particles in the corona and in the interplanetary medium for a few case studies. This link between particle acceleration and jet remains not well understood. We don't know exactly the timing between those. We also don't know how often they exist. Close to the sun, in situ and remote sensing observation with Solar Orbiter and Parker Solar Probe, of course, still combined with radio observation from ground-based instruments, will provide new observations of faint events, such as coronal jets, which are much fainter than the big flares we often study. And this will be an opportunity to visit those open questions. And again, because to study this process from a statistical point of view and to address the wide variety of solar jets that can be seen in both observations and simulation, we need an extensive database. And we are starting to build this with a citizen science project that will be looking at the 3 or 4 angstrom AI data for jets. I will stop here and I will take any question now.
Thanks, Sophie. So now you have 5 minutes before end of your talk. You gave
Yes.
the possibility to issue a warning. So we, anyway, we open for questions and discussion. Please unmute your mic. And Judy?
Well, thank you. First of all, thank you for such a wonderful overview of the subject and the complexities in it. I agree with a lot of your points on the opportunity in particular to with the open questions that you bring up. I just wanted to point out that this question of the number of foot points is actually complicated, a lot more complicated if you look at the 3D picture. Those cartoons are kind of misleading because they are looking at 4-flux system or 3-flux system models, but in actuality, the embedded bipole really gives you, the inner flux and the outer flux. And so, for the ribbons, for the flare ribbons that accompany most of these events, and if you look at Pankaj Kumar's paper in 2019 of 27 coronal jets, you'll see that all of them had flare arcades, mini flare arcades associated with them. Those have ribbons, and so those are your 2 foot points that are elongated in the polarity inversion line direction. But the foot points associated with the outer ribbon, whether it's breakout or interchange reconnection, doesn't matter. Those are pretty much the same at that level. You really get a circular or quasi-circular ribbon. And so, if you look at it with time, perhaps the X-rays would show that. I don't know why they always show you this single point. But if you look at like 1600 or something like that, you get this huge ribbon. And I'm sorry to take up so much time, but I want people to think in 3D. That's it.
Yes, I think I've been biased by the X-ray point of view, hard X-ray point of view, and usually we need to integrate over time to get nice images, especially if the flare is kind of faint, and that's probably why we don't have the dynamic of the ribbons in X-ray.
Thanks.
Okay, good. Stephen, do you have questions? You are unmuted, I think. I cannot hear Stephen.
So I've got a question if there's...
Okay, go ahead.
Yeah, so this is to continue what Judy asked about. We've always kind of noticed that the foot points, the hard X-ray foot points, just in a regular 2-ribbon flare are a lot more compact than the extent of the ribbons would suggest. And so this is, I guess, an extension of that in this spine and fan geometry that you're seeing. But I had a different question. The question is about the quantitative comparison of the number of electrons that you have that are required for a type 3 burst and the number of electrons needed to produce an X-ray burst. This is a problem with a lot of history, and I don't think we're there yet in terms of being able to actually detect the electron beam and compare the upgoing beam and the downgoing beam. Could you comment about this, about the status of that comparison?
Yes, I think to my knowledge, we don't have or we didn't have yet the opportunity to have X-ray measurement directly from an escaping beam of electrons, and that is something that is very difficult to do with X-ray instruments that have only an indirect method images like RECI. I think STIX will probably not be able to produce those images if the foot points are visible. But if we want to compare the numbers, we need to see the foot points and as well as the electrons that are produced in the escaping beam. So that's something that is, to my knowledge, we only have prediction from comparing with the electrons that we detect in situ and that are associated with those type 3 radio bursts. So I believe we have at least 1 or 2 order of magnitudes possibly difference between those. So we could have maybe 10 or 100 less electrons escaping and still producing the type III radio burst.
Right. To continue that question and involve Judy a bit more, in this third foot-point, which is not the mini arcade that's formed in this spine and fan geometry, but in that third foot-point, would the reconnection theory not predict that that foot-point would have a comparable amount of energy as to the amount of energy going up because the reconnection is just pointing in two directions?
I'm not sure I understand.
Well, the jet, I mean, there's a reconnection, right? So, and it's shooting the electrons out and it's shooting the electrons down. And so, in principle, should that not be kind of symmetrical? Is there a prediction from theory
depends upon the local conditions and where it is in the current sheet and things like that. So I don't know, because our MHD simulations don't directly show you what the electrons are doing. So I think that's a very good question. The partition of what's going to one direction or the other. But a lot of times in a lot of the events we see, the spine is tilted over quite a bit, and so the downward moving stuff is in a different magnetic environment than the upward moving, etc. So,
and also the density, the height, density with height can change things. Clearly, if it's lower density above, you might expect the upper going outflow to be faster than the downward going.
Yep.
Yeah.
Sophie, can I ask a question? This is Jim Drake. So, for many years, we had great difficulty on the theory side producing power law tails on the energetic electron spectra. But recently, we've been able to do this for the first time, having really extended power laws. And, we found two things, I guess I would say. First is that the size of the event doesn't seem to be the major control factor. And I guess, given the data you showed, that might be consistent with what you said, because you showed that whether you get non-thermals did not seem to correlate well with how fast the jet was. The second thing we discovered was that the magnetic geometry is crucial, in particular, whether you have magnetic fields that are nearly antiparallel or if you have a very strong guide field. And the implication of that is if you're trying to figure out when you should get non-thermals or not in jets, I think it's important to try to figure out what the magnetic geometry actually is. And so that's not always easy, I guess, but DKIST is coming online. So I'm wondering if DKIST is going to help you guys in terms of diagnosing what's going on with these jets, or whether you've thought about that.
Yes, that's definitely something to look at. And I didn't mention it, but I'm also trying to look as a first step to look at the photospheric fields for those jets. In particular, I started to look at the ones that have a non-thermal part, and so this is work in progress. I don't have any results yet, but I think we are trying to look if there is, for example, magnetic emergence or magnetic I'm forgetting the word, when magnetic fields are disappearing. So to see if there is any dynamic that is common to those jets, and that are also often seen magnetic flake constellation. That's the one I was looking for, to see if, because we know those things have been reported as happening for jets, and so we wanted to see if it was something that was found particularly for jets with or without non-thermal energetic electrons. But yes, if you have any suggestion on what we should look for in the data, I guess that would be a good thing to know.
May I ask a question?
Yeah, please go ahead.
Yeah, so I have a sort of naive question. Are these coronal jets, are they related at all to the jets associated with switchback? Switchback's C5 solar probe. You know, because those jets sort of feel the solar wind. So can one rule out that they have nothing to do with coronal jets?
Yes, well, that's a good question that I'm also wondering about this. I don't have an answer yet. I think probably jets that are producing the switchback, maybe from a different scale, they might be a bit smaller. And I've been looking specifically at jets that have been associated with flares seen in X-ray. So I think here I have a bias in my approach because I'm focusing on things that produce flare activity. But
they're very fast too. They are 200-300 kilometers
yes,
per second.
some of them,
to the
yeah.
solar wind, relative to the solar wind. So,
yeah. So I mean, they could be related and could be similar processes. I think we have to work a bit more to know the answer to that.
thank you.
More questions or comments? Okay, it seems that everyone is muted at this point, which implies that there are no more questions and there are no more comments. In this case, let me thank our speaker and listeners for taking part in the event.
Thanks to everyone for joining.
And let me announce the next talk by Jim Klimchuk in 4 weeks in mid-January about coronal heating of magnetically dominated corona. So thank you very much, and the event is over. Thank you. Have a nice new year.
Thank you, Sophie. Nice talk.
Thank you. Thank you.
Yes.
Thank you.